Hello class. Today we're talking about developing efficient algorithms in our Java unit. All of our unit will be talking about data structures and how to create efficient data structures and what kind of data structures we need, how to use them. Big O notation describes the performance and complexity of an algorithm, what data format will work for our algorithm, and Big O is kind of the worst case scenario. So when we're working with data, we want to understand what kind of data structures we are dealing with. From a scientific standpoint, you'll learn a lot more about this data subject when you have a 4-year degree and after you've had an opportunity to maybe work on a software project or two with a lot of data. But for now, you need to be able to understand basic functional patterns. We're not trying to reinvent the world, just thinking about patterns. Are we storing data, searching for data, sorting, or what kind of data structures are we using? Some data structures are suited for different functions, and some are designed for very specific purpose. But no matter what, it gives you more tools for your toolbox. So when we're worrying about these data structures, how do we measure their efficiency? We use the Big O notation, the worst case scenario, to try to figure out what is the most performance efficient. The first Big O measurement is a constant runtime. This is where an algorithm just does one thing. So it doesn't matter how many records or rows we process, it's just going to do that one thing. The number of elements is irrelevant. This is a constant runtime. This is called O to 1. We don't do that very often, do we? Now in a linear runtime, this is when an algorithm compares the first element in an array or some element to every element in an array. So say for example, if we have 15 people that we're searching through, we can search through all of them for information much faster than we can a grouping of more than 100. So this makes our processing efficiency dependent upon the number, or n, that we're dealing with. So as our n grows, it's said to dominate. So the more we are processing, the longer things are going to take. This is O on the order of n, or order n. And this is a common situation for us, especially if we're searching through an array. So the most common type of array search that we'll see is a linear search. And a linear search is effective whether we have a sorted or unsorted array. And what we're going to do is define an element that we're looking for, and we're going to search each element in the array sequentially to decide if we found the element that we're looking for. This is very inefficient. By the way, here's an animation from our author. So in this animation, we see that we have a linear search going on. We have an array filled with numbers, and they're just kind of random. This isn't going to show up very good on my screen, but pretty close. So we have all these different values in our array. Notice that they're not sorted in any way. They're just out there. And we're going to search for the number 8. So as we take our first step, we'll see, oh, this value is 1. No, it is not equal to 8. So if we step again, we'll see this value that's really high, 20, is not equal to 8. So we're going to keep searching. Step. Is that equal to 8? No. Is that equal to 8? No. We're just going to continue looking through the entirety of the array, comparing each element to what we're looking for. Now we finally do find it at item 13. So our set here had actually 20 entries, 20 n's, but we didn't have to search through all 20 of them, but we potentially could have. So that's why this is an O to the order of n issue when we're talking about Big O. It's a linear search. Just search right down the line in an array. Next, we have an item that uses a logarithmic runtime. This is where runtime does increase as we increase the number of items to process, but it doesn't increase by the order we would expect it to. So every doubling of the occurrence of n causes some increase in resource requirements, but not a doubling. So let's look at an example of this type. That would be the binary search. So with a binary search, we're going to split our array into two pieces, like half. And this array must be in a sorted order. And the built-in sort method utilized in Java will use this kind of search. Basically, it's going to find the middle, determine which half is relevant, and continue its search that way. Let's look at an animation. In our binary search, our index entries, or our array entries, must be in order, because otherwise we can't split things in half. So this is kind of like the game on The Price is Right, where the person is trying to guess the amount something costs between a different range called high-low. So they might say, okay, your amount is between 0 and 500. And some users will say 1, 2, 3, 4. And poor Drew is out there saying, no, 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 you're never going to get this prize. Who wins? The people that use a binary search. So if Drew says, okay, the number is between 0 and 500, the binary searcher is going to say 250. And Drew's going to say, low. And they're going to say, let's see, what's between 250 and 500? 375. And Drew's going to say, low. And so they're going to be able to answer that question much faster, figure out the price to the item. So we want to be like the successful high-low player. Let's see it in action here. We're looking for the key of 8 again in our sorted array. And so we start right in the middle. And we say, is the key we're looking for higher or lower than what we found? In our case, it's lower, so we're going to eliminate the rest of the array. We don't need to search through it anymore. It's gone. Now we're going to split our low half in half and say, what about 5? Is the key we're looking for higher or lower? Well, in this case, it's higher, so we'll eliminate this lower part. And you can see, as we eliminate and do by half, we're going to find that answer very quickly, much more quickly than when we had to do our linear search, searching through every element in the array. So that's a binary search. And a binary search is logarithmic, or O to the power of log n. So our time is going to increase slowly as the set size increases. Now we can also have a quadratic runtime. This is exponential. And in an exponential runtime, an algorithm compares every element to every other element. So every doubling of the occurrence of n causes a quadratic increase in resource requirements. This is referred to as O on the order of n squared, or order n squared. So let's look at a selection sort. We're not talking about sorts in this chapter, but it's a good example of an algorithm that is a quadratic, big O. So in a selection sort, we're going to search the entire array to find the smallest value and then move it to the first position. Let's look at this YouTube video. Now, in this video, I'm not sure if you're going to be able to hear the sound. Let's check. So we may just have to watch it, and then you can come back and watch it on your own. Doesn't seem to want to do anything. So I'm going to escape out of that and go back to the PowerPoint. Oh, there he goes, of course, as soon as I give it. Let's see, is it just not working right with him in full screen? Here we go, he's finally opening the door. It took him a while to open the door on this one. I was kind of giving up hope. Almost a minute. Man, okay, so here's the guy. He's got some balls to sort. They each have numbers on them. He's right now, the smallest one he's found so far is 2. He's looking through this whole array to see if he finds any that are small. Oh, there's one that's smaller. but he's still going because he could still run into a smaller one somewhere. Okay, so now he knows that that one was the smallest. So now he's going to search through the whole array for the next smallest number. Now we've already found it, but it doesn't matter because he's going to continue searching, because that's how this algorithm works, that the only way he can be sure that he's found the smallest value is by searching the entire array. Okay, now we're ready for the third position in the array. Again, we're looking for something that is less than our current value. Less than, that one is 4. So now we can put the 3 in that position. So think about how you're coding this program, that you're having to keep track of where your current position is in your array as you're walking to the end of the array. So we have to have a couple of indexes going here. We'll let him finish. You can see at the end that it is still terribly slow. Now we have things in order, but again, we can't tell that until we walk the array and we make sure that we have no numbers that are less than our current number. And finally, our array is sorted, and that was the selection sort. Great. So in a selection sort, as you can see, we potentially would double our time, if not making it quadratic, as we added elements to our array. Now the Towers of Hanoi is another standard algorithm, and this looks like a child's toy. Do you remember the stacker here? We're stacking things. And the algorithm is, how do we move all of the items from one pole to the next pole? And as we move, if you notice, you'll notice you can never put bigger objects on top of smaller objects. Now in this little animation, they end up with the entire stack here on the end pole. Is that okay? Oh, I don't know. It just depends on how you're working with Tower of Hanoi. Now in class, we're going to get some Tower of Hanoi games out and look at them, because it's important to remember what this algorithm is dealing with. So I'm going to click on this video. It'll be a lot like the little short that we were looking at. This one uses 5, so they're going to start out. Let's say I put the small one somewhere. Oh, no, I can't do anything. Put the small one on top of the next smallest. And as you notice, we have to keep kind of making space for things. So we got to move it, then move some others back, move them around. And it takes quite a few iterations before we can actually get things in the right order. So this is the Tower of Hanoi. This algorithm will help us move things and reshape things. Okay, so this is a common algorithm you'll find in your text. Next is the sieve of Eratosthenes, and this is an algorithm for locating prime numbers. So this is also in our textbook. This algorithm is explained. As you look at the section in our book talking about prime numbers, this is also what your assignment is talking about. You'll want to do all 3 different variations so that you can call them for the assignment that's due on next Tuesday. So the sieve of Eratosthenes. So again, you have a bunch of numbers here, and we've already eliminated the number 1 as being prime. So now we're going to he's kind of pointing out to you that this could be your ending number. We're going to first go through and eliminate basically the number 2. It is unchecked at this point. When we check it, we find that it's a prime number. It's divisible only by 1 in itself. So now we're going to eliminate all of the numbers in our set that are divisible by 2. That took out a lot of them, right? Next, we're going to check our next unchecked number, which is 3. Again, it's prime because it's only divisible by 1 in itself. So we're going to eliminate everything that is evenly divisible by 3. And as you can see, when you're working with this one, being evenly divisible is important. We start out with that at the very beginning of programming, working with the modulus operator. Okay, so the sieve of Aristophanes is going to slowly eliminate numbers so that the only ones that are left are the ones that are prime. Again, we do have that in our textbook, and you can come back and watch the rest of this video if you like. Another algorithm that's presented to us is the divide and conquer. So when we're working with divide and conquer, we are working with finding the closest pair of points. So we may have many pairs of points. In this example, they're convex hull points, and we want to find which one is the closest pair of points. And this algorithm uses Santa's dirty socks, and we have to hear the sound or it just won't make any sense. So I'm going to let you listen to this one on your own. Please do. And then lastly, 8 queens. And again, all of these algorithms are presented in our chapter, and the 8 queens video, again, will require sound. So I'll post this for you, this presentation. If you'd like to know a little bit more about Big O, and our book definitely gets pretty intense into the subject of the Big O notation, Code Academy has a new course on Big O. There's also an intro here that Rob Bell has created that talks a lot about it. I'm going to click on the Code Academy course. If you haven't already created a Code Academy account, you probably want to create one and just have it handy. Now, the Big O course on Code Academy is very short. If you click at the table of contents, it explains efficiency to you, and then it has a few items. So I would strongly recommend that you review the Code Academy course, but it's not required. That's it for our talk today. As you work with your assignments for this chapter, let's go look at your modules. I hope the Unit 1 exam was okay. I know the exams can be hard. We are in week 7, and so as you look at week 7, we'll be talking about data structures, just like we were looking at in our presentation. Your assignments are all prime numbers up to a certain number. Please be sure to look at the instructions in the assignment, because I don't want you to do exactly what they say to do in the book. And then in 2214, you're going to be comparing some different execution times. Now, for both of these, or at least for the prime numbers up to a certain number, you're going to need to know a little bit of information about writing a binary file. So in Ravel, I've also given you access to chapter 17, the binary I/O chapter, and you'll find it to be pretty short, so it's not going to be a problem to be looking at this chapter while you're working with chapter 22. But you're definitely going to need some information out of that chapter 17. Now, as always, please email me if you have any questions. We can work something out to get together, or Skype if we need to work on a program. I've been grading a lot. You guys are doing awesome. But please let me know if you're having any problems. Thanks.